In this lecture, we'll combine ideas from the theory of prime numbers and modular arithmetic to develop an extremely powerful, important, and counterintuitive application: public key cryptography. We'll open with a brief historical overview of ciphers and the need for encrypting messages. And then we'll consider the seemingly ridiculous question: is there an encryption method in which everyone can publicly announce the encryption scheme to code messages, yet only the receiver can decode messages? The surprising answer is that such a public key encryption scheme does indeed exist, and it offers a currently unbreakable coding method. In fact, the use of this encryption scheme is found every day in electronic communications of sensitive materials. Here we'll offer an intuitive introduction into the ideas behind this counterintuitive coding scheme and resolve the paradox in which everyone knows the encryption process, and yet only the receiver is able to decode the encrypted messages. The main theme behind this modern method is a 350-year-old result due to Pierre de Fermat, involving primes and modular arithmetic. The mathematical secret exploited in this coding method is the reality that factoring large natural numbers into primes is, in practice, extremely difficult, if not essentially impossible. Well, I want to open our discussion with a brief historical overview of secret ciphers. Throughout history, people have had a desire to keep certain information hidden from other people. Communications involving business transactions, national security, military plans, and even some romantic trysts needed to be kept secret from various parties. The earliest known example of cryptography was found in Egyptian hieroglyphics around 2500 BCE. Now, these may have been more for amusement than actually for secret communication. The earliest simple substitution ciphers, known as monoalphabetic substitution ciphers, may have been used by Hebrew scholars around 550 BCE. In a monoalphabetic substitution cipher, one letter is substituted for another. For example, every occurrence of the letter A might be replaced by the letter W, and all B's might be replaced by the letter M, and C's might get replaced by the letter R, and so forth down the alphabet. With this particular scheme that I just made up, the word cab, C-A-B, would be encoded to read R-W-M. Well, a Caesar cipher is a special case of the monoalphabetic substitution cipher in which each letter is replaced by the letter a fixed number of positions down the alphabet. For example, if we replace A by C, notice that C is two letters away from A, then B would be replaced by two letters away from it, which would be D, and C would be replaced by two letters away, which would be E, and so forth all the way down the line, all the way down to Z. And when we get to Z, we come back onto the alphabet. So for Z, we go two letters later, which would be AB, it'd be B. So Z would be replaced by B. Well, the Caesar cipher is named after Julius Caesar, who, in the 1st century BCE, used such a cipher with a shift of 3 to communicate with his generals. Now, such monoalphabetic encryption schemes are very easy, in fact, to break. Well, cryptography was known in India by the 1st century CE, during the time of the famous Kama Sutra, in which encryption was actually suggested as a method for secret communication between lovers. So here we see a wonderful example where the everyday passion of human beings actually gets melded with the passion of number theory. Quite exciting. Well, before leaving this historical overview, I wanted to briefly highlight some of the ingenious machines that have been invented to encode and decode messages. Now, the ancient Greeks used what are called transposition ciphers, in which elements of the text are rearranged according to a particular scheme. Now, they actually used a tool called a skittily to encrypt and decrypt messages. And I thought I would demonstrate it. So a skittily is basically just a wooden dowel. Sometimes they have flat faces here, but a wooden dowel. And what you would do is you would take either a long strip of parchment or a ribbon or paper, and you would wrap the paper or the ribbon around the dowel. So if I were to do this, I would see this, and you could see that this thin sheet of paper has been wrapped around. In this case, it's actually a ribbon that's been wrapped around. And so now I could actually write my message on here by writing a cross. And then when I get to the end of the line, just turn a little bit and write more, and turn a little bit and write more, and write my message. So for example, I've actually done this in advance. This is like one of those cooking shows where they do it in advance, but you take a pen and you write the message. But if you come here, here's my message. The message says, number theory is true beauty. Excellent message. So now the message is written here, and what I would do next, you see, is I would remove the ribbon, which I'm doing live here. And it's not easy to do. This coding is not easy. No one ever said coding was easy, but I'm doing it right now live. And now you would remove it, and when you untangle it, you see, you get this list of letters. In this case, it begins RYEYERUTBORUM, and then we just would write that out just as a row, and that would be the encoded message. And the person who receives this, we'd have to agree in advance, by the way, the thickness or the diameter of the skittily. And so then the message is put on a similar ribbon and then wrapped around the skittily, which is the same diameter. So the letters then line up, and all of a sudden that peculiar screed of letters turns out to make sense. Number theory is true beauty. And so we see it. Now, the interesting thing, by the way, here I just want to comment on is that notice that we're going around cycles. So it's almost like doing arithmetic modulo some number, division mod something. Now, another wonderful device that I want to share with you is the Jefferson disk. Now, this was an encryption and decryption device involving circular disks invented by Thomas Jefferson in 1795. Jefferson was quite, as you know, a clever person. And actually, variations of the Jefferson disk were actually used by the United States Army from 1923 through 1942. So I want to give you a quick little sense of what this is, because it's so wonderfully clever. So what we have here are disks, and on each disk what we see is the letters of the alphabet written out in some random order. And you can see, and the disks, each disk has a different random order to them. So it is a random collection of disks, random collection of letters, and so forth. And what you would do is your friend would have the exact same set of disks with the letters appearing in the exact same orders. And if we want to send a message, let's say you want to send the message math. So I have M, and then I find A, and then I look for T. Do you see? T, there's T. And then I need H. Let's see if we can find H. H. So, whoops. So I have M-A-T-H. So I put them together, and that spells out math right here on this line. And now what I do is I hold them all together, and I just turn all in unison until I get to any particular line, let's say right here, X-S-I-K. And that becomes the encrypted message. Our friend gets that, doesn't know what to do with it, so puts in XSIK on her disks and just turns them around until she finally comes upon a word. Ah, math. That must be from Ed. Well, there you have it. So a really ingenious way of actually producing encryption and decryption, and in fact, very, very useful. Well, in fact, the idea of using disks and cogs led to one of the most famous encryption devices known as the Wehrmacht Enigma, used by the Nazi military before and during World War II. Now, the Enigma was so complex that for some of the models, the number of possible rotor configurations actually exceeded 10 to the 22nd power, an enormous number. Incredibly, the Allied forces were able to break this seemingly impossible encryption scheme. And the great British mathematician and computer scientist, Alan Turing, was a key figure in cracking the Enigma. Well, long before Turing and his team broke the enigma in the 1940s, people have been working hard to break secret codes. The first systematic work in code breaking may have arisen from an in-depth religious analysis of the Quran around 800 CE. Arabs developed the method of frequency analysis to break codes. This is where you look for the letters that appear the most often and then gain some information from that. It's a very effective way, in fact, for monoalphabetic ciphers, breaking them, and represents what may be the earliest recorded work in probability and statistics. So, for example, in the English language, we know that the most popular letter is E, and then followed by T, and then A, and O, and I, and N, and so forth. So if you see a message that's in this monoalphabetic encryption scheme, the most popular letter probably would be an E, and then you could work from there. Now, frequency analysis makes monoalphabetic ciphers easy to break for the educated user. And a lot of people know this because this technique is often applied in the recreation of solving cryptoquote puzzles in the newspaper. So we've seen these things before. Well, in all the coding schemes that we've considered, there's a basic reality. We must trust our friends and allies. They know the biggest secret of all, the encryption and decryption methods for sharing confidential information. Now, our friends might be totally trustworthy, but if they accidentally lose the coding instructions, say for example, if the code book were to fall out of your trusted friend's pocket, or if someone were to break into their house and steal the secret, then the encryption system's security would be breached. Okay. In the basic ciphers that we've actually considered, to decode an encrypted message, one reverses the encryption process. Thus, if people know how to encode a message to us, then they also have the power to decode other messages. Well, wouldn't it be great to have a coding scheme so that when people use it to send us messages, the encoding process is easy for them to use, while at the same time, we're absolutely certain that we're the only ones with the ability to decode the messages. So, in this fantasy cipher, if you will, we wouldn't have to trust our friends at all. If they lose the code book and it gets into the wrong hands of undesirables, it would not jeopardize the coding scheme at all. In other words, ideally, in our fantasy cipher, knowing how to encode messages would not provide any information as to how to decode the message. Well, if this fantasy were real, then there would be no need to keep the encoding process a guarded secret. Instructions describing how to encode messages could be made public, and only the decoding process would need to be kept secret. In fact, in this fantasy, the encoded messages themselves could be made public as well. Our friends could take out ads in the New York Times with an encrypted message directed to us. Everyone would see it, but we'd be the only people that would know how to decode it. Well, the problem is, if a nemesis of ours sees a secret message sent, let's say, in the New York Times, why couldn't he take the encryption process, which we ourselves made public, and just run that process backwards to decode the message just made for us? Well, this is a problem. And to make this fantasy a reality, we would need to have a secret hidden within the public encryption process. So even though we make this process public, out there in this public announcement, there's something secret. Well, we're now ready to apply the number theoretic concepts that we've seen so far to show that just a crypto fantasy can be a reality. The main question remains, how can the encryption scheme be at once public, everyone knows how to encode messages, and private, only the rightful receiver can decode the messages? Such amazing ciphers are known as public key codes because the key for encryption is made public. Well, we'll make our fantasy a reality by combining the concepts of prime numbers, together with modular arithmetic in an extremely clever and elegant way. Now, in the next lecture, we'll offer the specific number theoretic details that make this amazing encryption scheme. But for now, I want to offer an intuitive introduction to the ideas behind the fantasy encryption method so that we can reconcile the seemingly paradoxical scenario in which things are at once public and private. Well, we'll begin with a metaphor that captures the idea of this modern encryption scheme. So let's suppose that we take a brand new deck of 52 playing cards, and so here, by the way, is a bunch of playing cards, and you can see that the brand new deck, because they're beautifully in order, and there they are in order. You can see them all like little soldiers lined up, 52 of them, and there's the ace and so forth all the way down the line. Now, if I were to take this deck and perform 8 perfect shuffles, which are also known as faro shuffles, that means that I cut the deck exactly in half, 26 and 26, and then perfectly shuffle one the other, and alternate without messing up at all, without making a mistake. If I do that 8 times, make 8 perfect shuffles, so 1, 2, 3, and so forth down to 8, then if I look at the cards, magically, they'll actually return to their original order. It's absolutely amazing, in fact, and I urge you to try this for yourself. But if you try this, you have to be able to perform 8 perfect shuffles in a row. Well, suppose now that we performed just 5 perfect shuffles. Then the order of the cards would look thoroughly mixed up without any semblance of pattern or structure. However, we know a systematic method that would return this jumbled mess back to a familiar, less chaotic pattern. We just perform 3 more shuffles, bringing the number of shuffles up to 8, and voila, the cards are transformed from a random mess back to their original order. Notice that we could employ this shuffling idea to produce an encryption scheme. Our friend could write her message to us one letter on each card. So she could say, you know, M-A-T-H, and so forth, and write the message. And then she would just shuffle, perfect shuffle, a certain pre-agreed amount of times. For example, let's say 5. So she performs 5 perfect shuffles, and then she delivers the deck of cards to us. Well, if anyone looks at them, it just looks all jumbled, but we know exactly what to do. We would shuffle perfectly 8 minus 5, or 3 times, and then we would be able to read the message that she sent us. Now, of course, if we were to use this encryption scheme, then anyone sending us a coded message could decode any other message sent to us as easily as we could. Easy, assuming that we can do perfect shuffles. Well, to have such a scheme truly fulfill our encryption fantasy, we would need to first figure out how to mathematically shuffle our message like a deck of cards, and then figure out how to make that shuffling process public without allowing others to unshuffle our message. Well, here's the moment where we introduce our number theory. The public feature arises from the fact that factoring extremely large natural numbers is impossible for all practical purposes, despite the reality that we know that such a factorization is possible in theory. So now we're going to start to make a distinction between practice and theory. To see the basic idea behind this public versus secret dichotomy, suppose that someone announced the number 6 and also revealed a secret. The secret is that this number is the product of exactly 2 primes. Well, can we uncover the secret? Well, of course. 6 equals 2 times 3. There. In some sense, we just kind of broke the code. Well, what if instead of 6, the announced number, that's the product of 2 primes, was 91? Can we break this code? Well, with some thought, maybe a little bit of arithmetic, we could figure out that 91 actually is 7 times 13. And thus we broke this code as well, although it took us a little bit longer. Well, what if the announced number was 2,911? Can we break this code? No, not so easy. But if we use a calculator or a computer, then we'd be able to discover that 2,911 actually equals 41 times 71. We broke that code too. Well, what if the announced number was a 100-digit number? For all practical purposes, even knowing that this number is in fact a product of exactly two primes, we personally would have no way of determining what the two factors are. In fact, even computers have limits to the size of numbers that they can actually factor. Factoring is hard even for computers. So this would be a problem even for computers. Well, in this way, notice that we can both announce a piece of information publicly, namely this enormous number, and yet from a practical point of view, within that public information is a secret that only we as the receiver know. This reality is how individuals will be able to announce an encryption process without revealing the decryption process. To encrypt messages, people will need only use the huge natural number. However, to decrypt or decode an encoded message, the receiver will need the prime factors of that huge number, which for all practical purposes is a true secret. Now, instead of writing our message on playing cards, we'll convert our message to numbers in a very simple way. We'll replace the letter A by the number 01, the letter B by the number 02, and so forth. So every letter in the alphabet will be replaced by a two-digit number, even all the way out to Z, which will be replaced by the number 26. Now, in order to shuffle our messages, we won't shuffle playing cards. Instead, we'll shuffle numbers by use of an important number theory theorem due to Fermat. Pierre de Fermat was a 17th century French lawyer who explored number theory as a leisure activity. As a result, he rarely published his important scholarly work. His body of work comes to us from his personal notes and correspondence with other mathematicians. As we've noted in a previous lecture, he would provide very little, if any, details into the proofs of his assertions. There were and remain mathematicians, including Gauss himself, who doubted if Fermat had complete proofs of all his mathematical assertions. Many of his claims were not resolved until hundreds of years after his death. Still, Fermat's contributions to number theory were enormous. One of Fermat's assertions was extremely stubborn in that no one was able to prove or disprove it. Since it was the last assertion of Fermat's that remained unverified, it became known as Fermat's last theorem. And we'll study this famous question and its eventual solution that required over 350 years in the making. We'll discover those ideas in lectures 14 and 18. Well, from the point of view of ciphers, Fermat produced an extremely important and useful theorem involving the prime numbers that holds the key to our cryptography conundrum. So, as to distinguish this important result from his so-called last theorem, this result is known as Fermat's little theorem. Informally, Fermat's little theorem asserts that if a number having a particular form is divided by a prime, then the remainder will always equal 1. Well, to inspire the precise statement of Fermat's little theorem, we'll consider all possible non-zero remainders when dividing by the prime number 5. So those non-zero remainders would be 1, 2, 3, and 4. Well, we'll now consider the remainders when we first multiply these four numbers by 2 and then divide by 5. And then we'll repeat this process with the new list that we get. So here's what we'd see. We start with 1, 2, 3, 4. We multiply them all by 2. So we see 2, 4, 6, 8. Now we consider their remainders when we divide by 5, or in other words, we consider these numbers mod 5, to use the language of the previous lecture. And we'd see that the remainder when 2 is divided by 5 is 2. The remainder when 4 is divided by 5 is 4. The remainder when 6 is divided by 5 is actually 1. We have a remainder of 1. And when 8 is divided by 5, the remainder is 3. So our list 1, 2, 3, 4 has been transformed into 2, 4, 1, 3, which notice is just a scrambling of those numbers. Now, let's repeat the process. Take this list and multiply by 2. So we get 4, 8, 2, 6. When I consider the remainders when we divide by 5, we would see 4, 3, 2, 1. Now we repeat. We multiply that by 2, and we see 8, 6, 4, 2. When we look at the remainders now, when we divide by 5, we see 3, 1, 4, 2, which notice again is just a scrambling up of 1, 2, 3, 4. And then if we do it again, we see 6 doubling. We see 6, 2, 8, 4, which if we look at the remainders when we divide by 5, we see magically 1, 2, 3, 4. Namely, these shuffling of numbers returned us back. Well, if we now just focus on the list of remainders we just found each time, and forgetting about the doubling process, we first see 1, 2, 3, 4. And then we see the shuffle 2, 4, 1, 3. And then we shuffle again and see 4, 3, 2, 1. Then we shuffle yet again and see 3, 1, 4, 2. And finally, and magically, we return back to 1, 2, 3, 4. So notice how this process does genuinely shuffle the numbers 1, 2, 3, 4 until we return back to the original order, exactly like shuffling the deck of cards 8 times. Well, since we're multiplying by 2 repeatedly, that's what I decided to look at in this example, let's focus on the values in the second location. Those numbers represent the remainders when different powers of 2 are divided by 5. Well, those remainders are 2, then 4, then 3, then 1, and then back to 2. In other words, 2 times 2 times 2 times 2, or simply 2 to the 4th power, must have a remainder of 1 when divided by 5. Okay, so 2 to the 4th has a remainder of 1 when we divide by 5. Well, Fermat generalized this last observation. And Fermat's little theorem actually states that given a prime number p and any natural number a that's relatively prime to p, so p doesn't divide into a, then when we divide a raised to the p minus 1 power and we divide that by p, the remainder equals 1. And we can actually phrase this in the language of congruence and use the congruence notation that we introduced. And we'd say that a to the p minus 1 is congruent to 1 mod p, which means that the remainder, when we take a to the p minus 1 and divide it by p, equals 1. In our previous example, we found that 2 raised to the power 5 minus 1, which is 4, is congruent to 1 mod 5. Well, as a further illustration, still with the prime p equals 5, we consider the number 3 and compute 3 to the 4th power, which we can actually do. That's 3 times 3 times 3 times 3, which is 9 times 9, or 81. And if we look at 81, we can actually see that that has a remainder of 1 when divided by 5. In fact, without any calculation at all, we can instantly produce the remainder when 5 is divided into 777 raised to the 4th power. Now, let's think about this. Let's look at the number 777. Is that relatively prime to 5? Well, if it has a factor of 5 in it, then it has to end in either a 0 or a 5. This ends in a 7. So we know that this number is relatively prime to 5. And so we can actually apply Fermat's theorem since I'm raising 777 to the 5 minus 1, or 4th power. So the remainder I can automatically announce equals 1 when divided by 5. In other words, no division was required. We were able to say the remainder. Moreover, the remainder when the prime 29, say, is divided into 1,000,000 raised to the 28th power must equal 1 for the exact same reason. The only primes that divide into 1,000,000 are 2 and 5. And since the prime 29 doesn't divide into it, it's relatively prime. If I raise 1,000,000 to the 29 minus 1, which is 28th power, I automatically know from Fermat's little theorem the remainder is 1. Well, Fermat first stated this result in a letter dated October 18th, 1640. And as usual, he did not include a proof. Instead, he wrote the following, which I want to share with you. He writes, "I would send you the demonstration if I did not fear it being too long. And we'll see this is actually a recurring theme when we come back to Fermat's last theorem. We'll hear a similar, although slightly more poetic version of this. Anyway, the first published complete proof of this theorem is actually due to Euler from 1736, so it took a while to actually nail down the proof. In the next lecture, we'll actually apply this historic theorem about primes to the modern technological world of communication. Now, it may seem a bit mysterious right now as to how we'll apply Fermat's little theorem to generate an encryption scheme. But I want to not only celebrate that in the next lecture, but also notice that we're going to pull almost every topic from number theory that we've explored together and pull them all into one collective whole to form this wonderful, interesting application that drives our technological age.